Good afternoon, everyone. I am Lorenzo Giuliano Papale and I'm a researcher at University of Rome, Tor Vergata. And my field of study is remote sensing data processing and application development using remote sensing data and artificial intelligence techniques. And now we are going to spend a few hours together, and we were going to do an exercise concerning wildfires and artificial intelligence. And starting from the link I shared with you, the link to the Google Drive folder, you can copy it with Ctrl C, and then you can go here and paste the link, press enter, and here you have the shared folder. Right click on this title and press on add shortcut to drive. My drive, add shortcut. And if you go on your drive, you will find the shared folder. Okay, let's go inside the folder and open the first notebook. I have split the exercise into notebooks. The first one is related to dataset generation and preparation, and the second one is related to the machine learning model design and development. So we can start from the first notebook, double click on it. Okay, so first of all, I want to spend few words about the topic of forest fires, since these dangerous and frequent events have become a critical phenomenon discussed by the international community. And as visible in this map provided by the European Environmental Agency, the increase in the fire weather index is strictly related to the climate change impact. So in this map we can see a projection of a possible future scenario with an increase of 2 degrees due to the global warming. So the map suggests how the efforts to fight against these critical events must be consolidated and possibly improved. So what remote sensing can do? Concerning the contribution of remote sensing, 3 stages can be identified from the literature. So remote sensing has demonstrated to be a valuable instrument for fire detection, and this technique is based on the hotspot detection around the world with satellites. Then the second stage is the damage evaluation, in particular the burn area mapping, and the third stage is the fire risk estimation. And this process has a crucial role in fighting against forest fires. But for today, the exercise will focus on damage evaluation stage. So we will perform a burned area mapping using Sentinel-2 data and artificial intelligence. Okay, so now this scheme represents the difference in spectral signature between healthy vegetation and burn areas. Indeed, a decrease in the near-infrared reflectance here in this portion of the electromagnetic spectrum is and an increase in the shortwave infrared reflectance occurs after the fire. So the idea is to exploit this behavior in the spectral signature, this difference, through a combination of the Sentinel-2 bands. But we will see it in more details. Okay, so concerning the approach, we will start from a small collection of fire events. And in the following tables, we can see for each fire event the date and also the area expressed in hectares. And here also we can see these fire events in this map. So the area of interest is the Mediterranean Europe. So the shape files of these fire events can be downloaded from the EFIS, the European Forest Fire Information System, and the burn area products can be retrieved through the online interface or by exploiting an API. But another option is to download run-through data from the Copernicus Emergency Management Service. And so the shape files are stored in a folder, in a subfolder of the shared folder that is named area of interest. Okay, summarizing for this exercise, Sentinel-2 data have been selected for their spatial but also temporal resolution, and the idea is to exploit the difference between vegetated and burn areas in terms of their spectral signature. And the approach is exploits the state-of-the-art spectral indices for burn area mapping, and these indices combine the pixel values in the different Sentinel-2 bands. And in particular, the indices will be computed for both the pre-fire and the post-fire images. And for Sentinel-2 data download, Google Earth Engine will be employed through its collection Sentinel-2. And this choice is motivated by the fact that with the Google Earth Engine it's possible to reduce the dimension of downloaded data in terms of spatial subset, but also by reducing the number of bands with just a few lines of code. And once the images are downloaded, the indices will be computed, and at the end, a GeoTIFF of the final product will be exported. So let's start with the exercise. First of all, we need to prepare the environment, the Google Colab environment for the exercise. So first of all, we need to restart the runtime, and if this is your first session, this step might be not necessary, but we can try. Okay, so here is not possible to click on restart runtime because this is my first session. But if you have the possibility to click on restart runtime, do it. Okay, so we can now click on this folder icon on this tab on the left and click on run of this cell to unmount. Okay, click on run anyway to unmount any possible Google Drive previously mounted Google Drives. And then now we mount our drive. Now the algorithm asks you to authenticate with your Google credentials. So you click on this link and then you click on your account and you can sign in. Now you need to copy this code and paste it in the notebook. So come back to the notebook in this box. Ctrl V and enter. Okay, the drive is now mounted. And if you click here on refresh, you will see that the drive icon will appear. And if you expand it, you can find the shared folder. Now you need to click on this box, on this to run this box, to set the current directory that is our shared folder. Okay. Now we can go on with the packages, installing and importing. And now, as you can see, we have some required packages and we're going to install them. Some of these packages are devoted to the vector and raster import and manipulation, and some of them are useful to perform Google Earth Engine functions. So we can run this box. And wait for the installation of all the required packages. There are also some other packages that are installed in the already installed in the Google Colab environment by default, so we don't need to install them. So these are few packages, but they are crucial for the exercise. Okay, now we can import all the packages and their functions by clicking on run. Here Google Earth Engine asks you to authenticate like before, as before. You click on this link. Again, click on your Google account and then allow and copy the code. Come back to the notebook and paste it and press enter. Okay, so for data request we need a small preparation in terms of tile and time interval selection. Indeed, as visible from this figure, Sentinel-2 acquires images with global coverage by splitting the world surface in square tiles. And so we need to find the correct tile for the geometry, the geometry of our fire events. And then the fire occurrence year and month are known from the table we have seen before, but we don't know the exact fire day. And this is because often wildfire duration can cover some days. So we will download the last image of the previous month as a pre-fire scene and the first image of the following month as the post-fire one. So if the fire occurrence is 2021 on August, we will download as a pre-fire image the last product of July, and as the post-fire scene, we will download the first image of September. So now we define the function related to the extraction of the spatial and temporal information for Sentinel-2 data request, but also the tile selection function and the time interval selection. The tile selection connects to the Copernicus Open Access Hub through the Sentinel API, and with the credentials it downloads for the input footprint the correct tile. This function is related to the time interval selection, and as input it takes the fire occurrence year and month, and it returns the time interval for the pre-fire and the post-fire scene. Then this is the function devoted to the extraction of the fire events information, in particular the year and month from the table we have seen before. So now we need to generate a geometry collection of the burn area products of our fire event. So in the following box, the shape files of the fire event will be read with GeoPandas Python package, and it is crucial to work with the same coordinate reference system. So all the shapefiles will be converted in WGS84 and saved in the directory. Then, since we operate with Google Earth Engine functions, we need to convert the shapefiles in Google Earth Engine geometry formats through the function shapefile to EE. And then, since the tile selection function takes the area of the region of interest as input in JSON format, the geometry will be converted again in this format. And eventually each fire event's geometry and the related tile will be stored in a dedicated dictionary. So with this box, as first we initialize an empty dictionary. Then through this loop we look for the fire event geometries inside the directory, and we convert them to the WGS84 CRS. Then, with this function, we convert the shapefile to Google Earth Engine format, and with this line, we convert the geometry to JSON format. Here, we store in variable C the related tile, and then we append the set name, the geometry, and the tile to the dictionary. Now, since if we go inside the shared folder and dataset and area of interest, we already have a folder. I have created a folder of the geometries in WGS84. So I have commented here these lines that write the geometries to the drive. So if you want, after the exercise, to store a copy of this notebook in your drive, you can uncomment these lines and perform your dataset creation procedure. So now you can click on Run, and let's see the output. Okay, I didn't click on this previous box. You need to run this box to store the functions. You can click to run this cell, and let's see the output. So for each fire event, the CRS is changed to the WGS84, and also the tile is defined for each fire event. Okay, now we can go on with data download and processing. So as mentioned before, we're going to compute some state-of-the-art multispectral indices from the Sentinel-2 bands. Sentinel-2 multispectral instrument collects sunlight reflected from the Earth within 13 spectral channels, and 3 of these channels are at 60 meters, 6 of them are at 20 meters, and 4 channels are at 10 meters. And the distribution of these bands against the wavelength of the bands is represented in this scheme. So here in this first row, you have the 3 bands at 60 meters, then the 6 bands at 20 meters, and the 4 bands at 10 meters. And in particular, as mentioned before, and as we have seen from the spectral signature difference between healthy vegetation and burned area, the idea is to exploit the short-wave infrared and the near infrared portion of the spectrum. And these are the 6 state-of-the-art multispectral indices that we are selected for this exercise. First of all, we have the NDVI, is a well-known index, is the normalized difference vegetation index, and it is very common index used to exploit the spectral signature of vegetation, since it is proportional to the amount of green vegetation, and it leverages the reflection sensitivity in the near infrared and in the red bands. Then we have the normalized Bohr ratio, that is a particular index that is designed for burn areas detection. The formula is very similar to the one of the NDVI, but we use the shortwave infrared instead of the red band. Then we have the difference normalized Bohr ratio, which consists of the difference between the normalized Bohr ratio computed on the pre-fire scene and the normalized Bohr ratio computed on the post-fire scene. And this index is crucial also for burn severity estimation, since the small values of this index indicate low severity, while high values indicate a strong damage caused by the fire. Then we have the normalized difference of infrared index, which is identical to the normalized Bohr ratio, but we use the other shortwave infrared band. And also we have the global environmental monitoring index, that is directly comparable to the NDVI, but it is less affected by the illumination conditions and the atmospheric effects. So this index can be considered more representative of the actual surface status. Okay, running this box, we define all the functions computing the multispectral indices through their formulas. So we click on run. And okay, so now we can go on with Sentinel-2 data download. And so in the following box, the pre-fire and the post-fire scene will be downloaded through a request to the Google Earth Engine collection, and the indices will be computed. And at the end, once the two products are processed, final GeoTIFF containing the multispectral indices will be exported to a folder in Google Drive. So here we define the train folder that we can find here inside the dataset folder. Since this train folder will be used to train our artificial intelligence model. So we define the folder, and then we define a function, multispectral indices, that for each set name, so for each fire event, it computes the year, it reads the year and month of the fire occurrence from the table. Then it computes the time interval, and by defining the selected bands of the multispectral indices we have seen before, it performs two requests. The first is related to the pre-fire scene, and the second is dedicated to the post-fire scene. And here in the request we can find the image, the Google Earth Engine image collection, and the geometry, and also some filters like the cloudy pixel percentage or the no data pixel percentage. And here, simply by adding these few lines of code, we compute the multispectral indices. So in these two variables, S2 collection prefire and S2 collection postfire, are stored the two collections, and from this collection we extract for the prefire collection the last image, because here we have false, so the last image of the previous month, and for the post scene we extract the first image of the following month after the fire. And then here we collocate the two images in a unique product, and then we compute the difference normalized Born ratio, since it is the difference between the normalized Born ratio of the pre-fire scene and the post-fire scene. And at the end we export the product with a resolution of 20 meters, but we can also export the product with a resolution of 10 meters, but for this exercise, due to the limited random access memory, we will use 20 meters. And then I have commented here task start, since in the folder train we already have all the folders with the computed images. So we can click on run, and the function multispectral indices is defined, but now we need to call it for each event in the dictionary. So we click on run. And here we can see how for each fire event is defined the fire occurrence, and it is identified the pre-fire product and the post-fire product with the specific tiles. And here we have the list of the bands of the pre-fire image and the post-fire image, and now we have the list of the bands of the final products, which includes the difference in the normalized Born ratio. So it takes some minutes, but we already have the file in our train directory, so we can click on stop to interrupt the execution. Okay, now we have our images inside this folder train, and since the machine learning model, the artificial intelligence technique, and in particular the Python package for machine learning applications, requires the ground truth image as a raster, but we have the ground truth, as we have seen before, in shapefile format. So we need to convert from vector to raster the reference data, the ground truth data, through a rasterization process. So the output of this this procedure will be an image with the same dimension of the Sentinel-2 downloaded scene, but with a binary format of the image, where 1 means burnt and 0 stands for unburnt. So we can click on run, and to define the function which reads all the shapes inside the geometry, and with this function it rasterizes the geometry, and then it saves the file. And now we can call the function, but since in our folder I already have computed the rasterization process, we can also jump to the next box, since in each subfolder in the train folder, for each fire event we have the image file with the multispectral indices and the label file for each fire event. So let's visualize these two images. So the following box is devoted to a visualization example of the created dataset, and in particular ground truth data, which is recognizable from the label written in the file name, and so we will visualize the ground truth data and one band from the image from the Sentinel-2 data contained in the multispectral indices. In particular, we will visualize the difference in normalized burn ratio, and but it is possible to change this visualization, in particular the band, simply by changing the index of the bands. The last in the index is the difference in normalized burn ratio that has 11 as index. So we can click on run. Now is loading all the files, all the fire events, and here we have the plot of each fire event, the label, and the difference in normalized burn ratio for each fire event. And it is possible to understand how the spectral signature difference between pre-fire and post-fire scene highlights the burn area, and with this index it is possible to discriminate the burn area with respect to the surrounding area. Okay, so this part related to data download and exploration is finished. So we can pass to the next notebook related to the machine learning, so dataset preparation, machine learning design and development, and performances analysis.